At the outset, I thank the organizers for giving an opportunity to deliver a talk in this conference. This conference is mathematical modeling and data science. Today morning, we have listened to our friend Venkatesan about big data, how to analyze big data. Now, what is my connection with this conference? Whether my topic is also coinciding with, at least to some extent, the topic of this conference. For example, now we have data from the brain, landscape, waves, how to model them, and the high tide waves, how to model them. And then in electrical and electronic communication that you have waves, how to model them. Now these are all the physical situations. We have data, not numerical data, but whereas we convert it into numerical data and we want to analyze them. And what is the model you can fit into it. And in this connection, polynomials will play an important role to model these type of natural resources. And from pure mathematics point of view also, there are certain questions for which we have an answer through polynomials. Polynomials are very friend to us. In early days of our education, we started learning, finding the roots of the quadratic equation, cube equation, then degree 4, and what happened to the 5 and other things, whether we can give the answer or Galileo will give an answer. All these things are part and parcel of our education. Right? The problem really comes when the coefficients are random. How to solve them? Because the initial days they found it very difficult. Even for a quadratic equation, when the coefficients are random, following a simple distribution function, probability distribution, how to find out the roots? And what is that? How many real roots are there and then how many complex roots are there? Because they are all random, number of real zeros are also random. So if that is random, then how to measure this? The probability of the measure with respect, which is less than some constant. What is the bound for this? This is called the lower bound of the number of roots and then upper bound of the number of roots probabilistically. Because probability coefficients are probability, follow some probability distributions. Next, we concentrate on natural average. For example, the question here is, for example, we have crores and crores of data. As our Professor Venkatesan was telling about so many variables, even your Excel sheet will not be enough to accommodate all your data. You just find out the mean for such data. It's very difficult. So what is the way out? That is why we have big data analysis branch. And for which, what is the role of statistics and the role of data science? Then we have recent artificial intelligence tools, machine learning, all these blah 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 are coming under only statistics. But only on the strong foundation of mathematics, for which you need multivariable calculus, linear algebra, and classical probability theory. These are all the 3 essential components to study data science. So, nowadays we are not getting students for BSc Mathematics and Statistics. It is almost over. Only single digit number admissions are done. But it is a very danger. Very danger. Why? Mathematics education in any college, any university, any state, why? In any country, it is an indicator of the development of the country, development of this institution. Once you have that strong mathematics, then your college or your institution, university or your state will flourish. Now, I think administrators, they have to take suitable steps to propagate, to educate and to inspire and admit and then educate mathematics students. Okay, now this is the aged people like me are. Yeah. No, I used to give talks, this random polynomial, so many conferences, and I used to concentrate on only one aspect, namely polynomial of single variable. Now the question arises, even the calculation is very difficult. Calculation is very difficult. I will show you starting the difficulty from quadratic equation and then cubic equation, and then you will go for the nth degree equation, and then what will happen to that. So you cannot give the exact value, therefore we will sort for asymptotic value of this. It is well known that it is well known that the study of roots of random polynomials has become an active area of research among the most popular topics in mathematics. This field has motivation and application in many branches of mathematical sciences. Just now I was telling some of them. We need to remember the results of random polynomials. So first book on Bershauer and Sambandham. Professor Gopal was mentioning about the book. When he visited United States, he saw that book in the library. At that time, it happened in 1988, I think. Okay, and that book contains the contribution of my thesis chapter, and that is also the same chapter, same content, ditto. It is published in the book. And then followed by the Ferrament. Actually, the Ferrament is equation equal to some constant, polynomial equal to some constant. In stochastic process, it is called a level crossing problems. He not only used that equal to constant, he also introduced some polynomials. In that case, he started studying the number of crossings over the curve, not level crossing, it is called curve crossing. So this type of thing you can see that in the Ferrament book. And then what is the further development? These two books are now. The third book, we are trying, myself and Professor Sambandham, and that book contains further development. What are the different areas of random polynomials that we are developing chapter by chapter. I think it will take 1 or 2 years to complete that book. Shortly, I mean, if possible, if I breathe. Look at this. These are all the mapping of our brain. So when the mapping of this brain, what type of data, how to represent it, how to model it, that's one question. And then here, and then it is from also the same thing with the different positions. And geographical, these are all the geometrical locations that you can see it in our landscape, right? How to model them, these type of structures. The positions now at next, in statistical physics, quantized vertices in 2D rotating ideal Bose gas can be mapped into zeros of random polynomial depending on the atomic state. Nobody knows about when we study the roots or zeros of the polynomials or quadratic equations, they are nothing but the energy levels. In statistical physics, they are mapped into the energy levels, right? Now you think about the random character and other things, that how it will represent. Zeros or random polynomials are popping up in the many areas in physics, peak points of signals, then vacua in compactification of M theory. This is the thing that we are looking at in our contribution. Then Calati manifolds with flux, extremal black holes, peak points in galaxy distribution. And this type of thing you can see the astronaut Chandrasekhar's papers, right? Right. Now these are going to occupy in our book, proposed book. Now coming to that, here this random polynomial is the topic coming under random algebraic geometry, right? This algebraic geometry are interested in zeros of holomorphic sections of any positive holomorphic line bundle over any Kähler manifold. That means actually now we want to study the random polynomials on manifolds, right? On the real line we are moving to different topological structures and even algebraic structures, so that mathematics part will become tedious. I think for this type of audience, I'm sorry, when I talk about these random polynomials on manifolds and other things, it will be out of focus. So my point here is to give the motivation, how you have to go from one dimension to a higher dimension. And then later on you can think about, he was talking about the Banach space, Hilbert space and other things. We can think of polynomials on these structures, topological structures, or even algebraic structures. Algebraic structures in the sense that, for example, you take the Lie groups. On Lie groups, how these random polynomials will play. These are all further investigations. We need to do more things. Now recently we got the random harmonic polynomials. There's another branch, it has come up recently, by 2 or 3 years old papers. Okay, now let me start with interval real axis. It's a smooth function. Why we called it smooth? You can differentiate continuity, all these basic assumptions of calculus are assumed there. And consider the random variables xi with the mean, mu and variance defined on some same probability space. And the linear combination of this is f of k is deterministic function, whereas here this k is the random quantity. Now you have that structure, this is called the random function. The value of this random variable at each point is a random variable. Next, f of k equal to t power k, then it becomes an algebraic polynomial. Now if k is sin kt, it becomes a trigonometric polynomials. Right. Now, as far as algebraic polynomial is concerned, you are taking that minus into plus infinity. Because of the expression after simplification, this is split into 4 parts. 0 to 1, 1 to infinity, 0 to minus 1, minus 1, minus infinity to minus 1. This negative part is nothing but if you replace x by 1 by x, then the polynomial will be in the from negative side. So the 4 parts, now all these things when you study on one part, namely 0 to 1, then it is equal to studying on the other parts also. Therefore, it is 4 times 0 to 1 integral. So the entire computation simplified it to 0-1 interval as far as this random structure is concerned. And it so happened that as far as a random polynomial is concerned, the real roots are concentrating at 2 points. Concentrating at 2 points, -1 and +1, -1. But when the same thing, when you take the complex roots, right, then you take the complex roots, they are around the unit circle, right? And then when you take any area, when you to suitably define the polynomials, it is concentrating on the boundary of the region. Now here, we have taken the interval and then it is concentrating, the zeros are concentrating on the end points, right? And then when you take that circle, then roots are showing concentrating on the unit circle, boundary points, near the boundary points. Or when you take any set or boundary of any set with suitable conditions, and the roots are showing that concentrated on the boundary. So this is an analogous story. I think I am repeating this for so many places because it is useful for the students. Now when you look at the fundamental theorem of calculus, f of b minus f of a, this is equal to integration a to b f dash of x and dx. Okay. This fundamental theorem of integral calculus says this. That means you are integrating over the interval a to b, and then its value is given at only at 2 points, where these 2 points are end points. You take the interval AB, you are defined that differentiability and other conditions on the interval, but after evaluation, you are evaluating only at 2 end points. Now, you generalize to 2-dimensional. In the 2-dimensional part, what happens is, in the 2-dimensional integral, what happens? This is concentrated on the boundary. 2-dimensional integral expressed in terms of 1-dimensional integral. When you took the 3-dimensional integral, its value is expressed in terms of surface integrals. These are all the 3 theorems. Why that theorem is called fundamental, you will know now. Because after evaluation, the value is concentrated at the end points, boundary points. Now, Stokes theorem. Stokes theorem says integration over double integral gives the integration over the boundary line. Right? When you get to the third dimension, Gauss divergence theorem, 3-dimensional integral value is given in terms of 2-dimensional. That means volume integral, it is expressed in terms of surface integral. This is the idea coming from our fundamental theorem of calculus. That is why it is called a fundamental theorem. Okay. Now the same thing here, it so happened in random polynomials, zeros are surrounding -1 to +1. But when a complex variable, it is concentrating on the circle. When it again extends it to areas with suitable conditions, it is showing that on the boundary, right, delta. Now, these are all the developments. It is already existing in the literature, but nobody has analyzed this. What I am trying to say is, there is a formula given by an electrical engineer, not mathematician or statistician. Electrical engineer, Katz, and also Rice. These are the 2 fundamental papers, and they have given the complete answer. Earlier also they have studied. The problem started from 16th century. Here, and Warings is the first person to start studying this random character for the polynomials. So now the function f is called Gaussian. We know that the definition for Gaussian. When these xk's are normal random variables, mean k and variance sigma k. Then nf stands for number of roots, number of real root zeros, then expectation and variance. My work mainly on variance of the number of real roots. I took 2 years to complete one paper. That is from the part of this book. 2 years of work, only one paper. And we analyze this problem for dependent random variables on the correlation, constant correlation coefficients. Remarkably, what happens is that variance is reduced to half. Whereas in the ordinary Gaussian random variable, independent random variables, the variable is something like some row, but whereas in our study carried out at Annamala University, Sambandham's thesis itself, he only started analyzing this using dependent correlation coefficient for average number of zeros. He obtained that half, but I obtained is, of course, along with Sambandham, half of the variance. So, what is the reason for it, and other things are explained in the paper itself. Now, coming to the point, because in the negative side, when calculate, terms get cancelled. Therefore, it is half. Answer is coming in terms of half. Okay, motivation from the existing results. Already I told you so many motivation points. Situation triggers a question whether there are random polynomials whose zeros are uniform on the complex plane. These are all another type of question, for which now the answer is yes, it is possible. These observations motivate us to study, summarize and explore as results as well as new avenue for further investigation in the theory of random polynomials. The problem here is in what way you have to go. What are the problems you have to define? That itself is a problem. Problem for a problem. Right? It's a measure for a measure. Pleasure for a pleasure. Love for love. Right? Like that, this year we have challenging situations before us. We are not succeeded in all the attempts. Miserably failed in many attempts. That is why I never give this topic to my students. Because suffering for my sufferings. So I don't want to distribute it. Sometimes it may become a hard nut to crack. Really it is a hard nut to crack. The talk on random multiplication has been broadly bounds for the number of real zeros to start with. Average number of real roots because of the random character. Maxima and minima. Another one. Maxima and minima. How many maxima and how many minima? What is its average value? Average value means not exact. It is only an asymptotic value. Right? Asymptotic value, maxima and minima will tell you, suppose in a landscape, there are so many shallows will be there in the ground. How many of them are there on the average? Like that, the peak points in the hilly area, how to calculate this? Right? For example, now take the sea wave. Right? When a wave comes out, what is that peak point? These are all useful for engineers. Those who are in the marine engineers. Right? So the topic, it is a pure mathematics, but it has complete applications. Variance of the number of real zeros with the Woman's conditions, of course, vary. One may consult the book, of course, Burshard and Sambandham and Ferramand, right? I told you about these Ferramand's results. Now look at this. Let us start with a simple story. This simple story, you can find this as a problem in Carlin's book. For this problem, thanks to Uday Bhaskaran sir, he has also given one method of how to solve this quadratic equation with coefficients follow uniform random variable. Now this is the calculation point of view. Number probability of real roots of quadratic equation, b square greater than 4ac, 1 minus b square less than 4ac. That's all. Where a, b, c are uniform random variables. Right? Now this is nothing but the triple integral b square less than 4ac. That is where the crux of the problem. Uday Bhaskaran sir, he used a transformation of random variable technique to find out the solution for this. Remember, this is an exercise in Carlin's stochastic process book, not Carlin and Taylor, Carlin's original book. Now this is divided into two parts, and we got the after calculation will get 5 plus 3 log 4 by 36. But the proof will go to pages. Now the same thing, what will happen if it is minus 1 to 1? Right? Earlier uniform random variable 0 to 1. Now the question here is, sir, is it, suppose you assume discrete random variables. Results are there? Not many. Right? Of course, there are some results. Some results means only plus and Bernoulli random variables. People have analyzed this, and for which they have given 16 printed pages of Oxford and Littlewood paper. Excellent paper. Of course, there is a error in the lemma 14 of that paper also. Therefore, even I can say that even it is unsettled. Even though they have given mathematically very sound analysis, but we can use the analysis, a trick in that paper, but results are still open. Now here you obtained this. Now coming to this, another quadratic equation, this is a thesis, PhD thesis. The x square plus psi 1x plus psi 2x, where psi 1, psi 2 are random variables. In that case, how to calculate, or assuming different distribution functions, how to analyze this. The PhD thesis contains all the analysis part. Now coming to the cubic equation, ax cube plus bx square like this. Here after the calculation, it will end up with this type of integral 4 times. But when a calculation variance part, 9 in iterated integrals. Right? And in my room, I used to put all the papers spread over the envelope. Then I will put one part this, one part this, one part like this. This is how I did the calculation for the variance paper. And those days we are not having any Maple or MATLAB or any other software like this. We have to do only using pen and paper, right? Right. Evaluation of this is an open problem. Still there is no concrete answer for this, evaluation of this integral. But it is open to evaluate this integral. For random cubic equation, again, Soline's thesis, I think they have given 3 parts. The results are expressed in 3 sets. The one set is equal to empty. Other 2 sets they have given. In this thesis, you can find out the solution for this. Depending upon, I have given that as the 3 cases, right? The 3 cases results.
5 minutes, sir.
5 minutes. What's this? I have not even crossed.
Yeah. It is already 27 minutes, sir.
My God. Shall I read it?
Some final points, sir.
Finer points. My God. It started with the Descartes, you know. Then Stern's equation. These are all for discrete polynomials. Baring in 1982, he only started introducing randomness in the polynomials. Then 1943 onwards, we got that very concrete cake and rice simultaneously. Therefore, we call it cake-rice formula. Now, remember, I tell you one thing. Always you have to start from elementary things. How to catch a point. The point, if it is on the x-axis, when the curve passes through it, we call it a 0. Right. Normally, how to point out a point on the x-axis? Representation. And all the zeros, you take the representation. Now, you must catch. How? Use that Kronecker delta. Or direct delta function, not Kronecker delta, sorry. Direct delta function. Direct delta function will identify a point. Using that direct delta, another mathematical technique called change of variable. You take the Fourier transform of the direct delta function and then applying this change of variable, you will get this equation. Number of roots is expressed in terms of 2 by epsilon, A to B, indicator of this, and then f dash of 0 t after change of variable. Yeah. When you take that small intervals around the zeros, then you can calculate number of points you can identify. How this? Delta naught f of t, f dash of t. And this is the basis. From this, you are substituting f of t is your random polynomials and probability distributions. Then thereafter, only basic idea is important. How you are going to catch the zeros on the real line. Right? Yeah. This is the formula. This is the characterized formula which resembles your b square minus 4ac formula. Our ABC here are polynomials and a differential. First derivative, second derivative like this. And whose values, as I told you, it is 1 by 4th of the number of zeros on the interval 0 to 1. Now here, after simplification, you will get this. Now here you have to integrate this integral 1 by 1 minus t square, because in one of my talk, one professor asked how you are getting log n in the number of real roots. Even prime number theorem also you get the log n. Right? These are all calculation of prime numbers. Now here it's zeros. Here also you get log n. That means it is very few real zeros are there. That is what it means. But surprisingly, you'll get 2 by pi log n, average value. This log n comes because of this. Depending upon the different situation, you will get the integration different values. So appropriate integral it is used so that you will get log n there in the answer. Now you are getting this log n because of that different integral values for the same integrand, right? Appropriate integral technique is used and then evaluated this 2 by pi log n. This is average number for Cox polynomial. And if the random variables are dependent, it is reduced to 1 by pi log n. Right? Same thing what happens to the variance. Variance also the same, we leave it off. Because, what I want to tell you is, crux. You take system of polynomials. For system of polynomials, what is the average number of real zeros? Now here the system of polynomials are system of random polynomials. Right? For system of random polynomials, you will be surprised to see the result. The average number of real roots is nothing but the Basut number. What is the Basut number in algebraic geometry? Nothing but the multiplication of degrees of the polynomials. Right? Now here, you are getting that for system of random algebraic polynomials, average number of real roots, the square root of Basut number. Right? I think. Yeah, expectation of n is square root of d1 multiplied by d2. They are all degrees of the polynomials. That is the square root of the Basut number. Basut number is nothing but the multiplication of degrees in algebraic geometry. Now here, same idea, but we are getting surprisingly the average number of real roots of a system of random algebraic polynomials is nothing but the square root of Basut number. Earlier we have for one dimension random variable you will get 2 by pi log n, but whereas here you are getting square root of the Basut number, right? Now the same type of exciting results are available for different type of structures. Random polynomials depend on algebraic structure, like for example Lie algebras and other fields are manifolds, Kähler manifolds like this. So literature is very fast, still it is growing. And recently, the same type of question will arise for harmonic polynomials. When you have the harmonic polynomials, my question is, what is the average number of real roots or roots for system of random harmonic polynomials? Same thing, like that subject is growing again and again, right? We are rolling back the same thing. That is why I use the word measure for measure. Right? Ideas for ideas. Like that it is going on, the subject is growing very fast. Right? I think, right? So that is my, though I could not give that entire thing. Actually, I started giving all the 4 sessions for, I thought it would be for 1 hour talk. But I cut down most of the slides. Then at least I can give only the fundamental idea of and only one new result that I want to show it to you is the system of random polynomials. Thank you very much for your patience.
Thank you, thank you. Thank you, sir. Thank you, sir, for your any clarification? I need one clarification. Small clarification. Thank you, sir. You said no. From the positive side, you are on x for the negative axis. You always take 1 by x. Correct?
Polynomial it is substitute 1 by x.
1 by x. Suppose I got 2, then 1 by 1 by the scale will be the same or it will be different?
No, sir. That when you replace the polynomial by 1 by x, it will become positive side to negative side. Same thing.
I thought it would be taking 1 by x.
No. No. When you substitute, when you.
Sir. Yes, sir. Yes, sir.
Regarding the zeros you are talking about, they are clustered around -1 and +1.
Yes.
Can you see any similarity or symmetric structure in these 2 points? Are they similar in their spread?
No. As far as these Kack's polynomial, namely, for example, you take the coefficients follow Gaussian distribution, right? Gaussian distribution, standard Gaussian. That the zeros are having the tendency to concentrate on +1 and -1.
But you said that you studied B of N of F and R.
Yes.
Variance.
Now here this is zeros, not average.
Roots.
Not house.
Sir. எனக்கு- கேளுங்க sir.
You
sir,
can ask
கேளுங்க
anything, sir.
See that 2 by pi log n, something astonishing result. Actually, it reminds me of the famous Stirling's lemma.
Ah.
Thank you, sir. Thank you.